Alright, welcome ladies and gentlemen. So I want to talk to you a little bit now about what we did yesterday, which was looking at the Lewis structures, formal charges, resonance. And I just want to clean this up before we start talking about geometry. So first of all, what's important is step number one is you draw a Lewis structure. Most Lewis structures, you know, they will follow the octet rule, but there's some that will go against the octet rule. So if you have hydrogen, boron, beryllium, these will not form an octet. Beryllium and boron, these two here, they will take the best structure based on formal charge. And the best structure based on formal charge is where boron has the single bonds, beryllium has 3 bonds. Boron has 3 bonds, beryllium has 2 bonds. So that's important to note. Then you have the ones that can have an expanded octet. So an expanded octet, those are elements that are silicon, phosphorus, sulfur, chlorine, and so on. We can have a lot of them. And there's two things with this. First of all, you draw the Lewis structure, and then if you need to, you add extra electrons to the central atom. And so we saw that in the example here with xenon, where we had to add 2 extra, and with iodine, where we had to add 4 extra. You could have something where you have phosphorus connected to 5 chlorines. All 5 chlorines will be attached to the phosphorus. They won't be where there's a chlorine attached to another chlorine. Okay, now there's then the muddy situations here where you could have, you know, do I violate the octet rule or not? And so we saw that with things like SO4 2-, or we saw that with XeO3. A lot of elements do this. Like for example, chlorate, ClO3-. We see that chlorate actually will do the same thing, where it forms 1 double bond. And when it does this, so chlorate has 7 and 24, that's 31, and 1 is 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 22, 24, 26, 28. I counted wrong. 18 and 7, 25, 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Sorry. 22, 24, 26. And so we'll get this structure like this, where there's a double bond here to that. And in fact, we could even do this, where we actually have 2 double bonds. And what this will do, if we look at the formal charges, these oxygens are 0, this oxygen's -1, and this chlorine is 1, 2, 3, 4, 5, 6, 7 is also 0. And so the formal charges get as close to 0 as they can. And so that really helps us to see this type of thing. Another interesting example is SO2. SO2, you would think it has a double and a single, but it turns out when people experiment with this and they actually look at the structure looks like this. S violates the octet rule because it can, but it also brings the formal charges down all to 0, and this is the more stable structure. So, you know, when we look at this, when we look at formal charges, so elements that can expand their octet may do so to minimize formal charges. We see it a lot with sulfur, but we see it with other elements as well. Okay, so let's talk about the molecular geometry. So this is one of the really important things you have to memorize. you have to know this chart. And this chart goes on for 1 page, 2 page, 3 pages, 4 pages. I believe that there are 13 different shapes that you need to know. Now, what are the shapes? Well, the shapes are, known as the Vesper shapes. And so the idea is you have the valence shell electron pair repulsion model. Valence shell electron pair repulsion, in short for Vesper. Vesper model. And what this says is that the electrons will spread out as much as they can to minimize their repulsions to one another. So let's go through this chart. When you have a central atom in gold here that I'm highlighting, I'll circle it, and it is connected to 2 other what they call domains, electron domain geometry. The electron domains will spread out as much as possible so that they can minimize the repulsions. If you look at my window where I'm speaking here, I can show you this with pens. If I have a central atom where I'm holding my finger here, and we have the electron domains, the electron domains will spread out to a 180-degree angle, and you'll have this linear shape. I don't think this is working well with the camera, though. I'm going to do this in class with you, but this just gives you an idea of what linear looks like. I'll redo this in the classroom. So when you have 2 connected atoms, and there are no lone pairs on the central atom, we can see that in example here, CO2. C is connected to 2 atoms, 2 oxygens, with no lone pairs. The electron domains will spread out. They'll be linear. They'll be a 180-degree angle. If you have 3 atoms connected, and I can try and show that in the camera again, I don't know how it's going to work, but I'll try. So we have our 2 connected atoms, and now I put on a 3rd atom, still not working. It causes these linearly arranged atoms to spread down into a triangle. And you can't see this, but this is my triangle shape I'll show you in class. And so this has 3 connected atoms and no lone pairs. This is where you get a trigonal planar. It's flat. The molecule is flat. It's in a triangular shape. It's about 120 degrees. Now, if I were to replace this top B atom up here that I'm highlighting with a lone pair that I'm circling down here, it still has a flat shape, but now they call it bent. So when you have 2 connected atoms and 1 lone pair, you're considered bent. And here's an example of a bent molecule, NO2-. Now, this lone pair up here, it takes up space. And when you have that lone pair taking up space, the angle between the 2 oxygens down here actually gets a little bit smaller. So the angle between the BF3s up here is 120 degrees. The angles between the NO2s is about 118 degrees. This again is to minimize repulsion. Well, what if I were to add 4 domains? 4 domains were into this tetrahedral family. 4 connected atoms and no lone pairs. The atoms will arrange themselves in a tetrahedron. This is now no longer flat. It has this trigonal pyramid at the bottom and an attached atom on top. To be tetrahedral, this has 109.5 degree angles. With trigonal pyramidal, we've replaced the B up top with a lone pair, and now we have NH3 with a lone pair up here. The angle gets a little bit smaller. It's 105. This is 3 connected atoms, 1 lone pair. If I have something where I have 2 connected atoms and 2 lone pairs, now I have 2 lone pairs up here. It makes the angle even smaller between the H's here, and it's about 104.5. This is all part of the tetrahedral family, but these are the actual molecular geometries. Up here we have trigonal planar. We have 2 specific shapes, trigonal planar and bent. Now what happens if I go ahead and I violate the octet rule and I add on 5 domains? Well, then I get these 4 shapes right here. If I have 5 connected atoms and no lone pairs, I'm trigonal bipyramidal. I have 2 angles. I have 120 degrees for these 3 B's here, and then I have 90 for those. If I add a lone pair instead of another atom there, I have 4 and 1, I'm considered seesaw. If I have 3 connected atoms and 2 lone pairs, I'm considered T-shaped. If I have 2 connected atoms and 3 lone pairs, I'm back to linear. This linear, though, is different from this linear. It's the same, shape, but the way that it forms, this one has two connected atoms, and 3 lone pairs. Now, if I go here to having 6 connected atoms, all of the angles become 90 degrees, and this is called octahedral. There are 3 shapes that you need to know for this down here. There's octahedral, and they call it octahedral, not hexagonal or something like that, even though there's 6. Because if you were to cover up this with like a paper mache and make a shape out of it, then you'd have an 8-sided object. If we were to replace one of these B's with a lone pair, we would have square pyramidal. And if we were to replace 2 of these B's with lone pairs, we'd have something called square planar. All of these, all the ones with 6 domains and 5 domains, violate the octet rule. They all go above and beyond the octet. So I expect you to memorize all these. Please spend time to do that. We'll talk more about these in class tomorrow. Thanks so much for watching.